Hello everybody, welcome back. So after sketching the general strategy for hypothesis testing for a parameter in the last video, we're going to take a very specific type of hypothesis testing. That is hypothesis testing for a population mean in which sigma is known. The population standard deviation is known. And we know the difference, right? Because from the last chapter, we have a different distribution if it's known and when it's unknown. When it's known, we can use a normal distribution. When it's not unknown, we have to use a t-distribution, okay, which is what we'll talk about in the next lesson. But here are the guidelines, and you really want to go over those guidelines and, well, not only memorize them, but have them with you whenever you evaluate a claim. First of all, you want to verify that sigma is known and the sample size n is the sample of size n is random, and either the population is normally distributed or n is greater than or equal to 30. And that last part, of course, it comes from the central limit theorem. We need to use that because we want because if this last part holds, then the sample means are also normally distributed. Okay. So that usually doesn't take too long. In all of these examples, it'll be easy to check that. Second part is to state the null hypothesis, H0, and the alternative hypothesis, HA, and identify the claim. So in this case, you'll be given a claim, and if it has some sort of equality in it, then it's the null hypothesis. Otherwise, it's the alternative hypothesis. Okay, and remember that the H0 and HA are complements of each other. Okay, so you're going to write both of them and identify the claim. Then specify the level of significance, alpha, that will be given to you. Okay, and again, the level of significance is the maximum probability that you're making a type 2 or a type 1 error. That is, that's the maximum likelihood that you'll be rejecting something that is true. Okay, then then determine the critical values, and in particular, are you using a right-tailed test, a left-tailed test, or a two-tailed test? And on the last video, you'll see that we did a lot of stuff with rejection regions. I think we made these. This is from the last video. So you'll be drawing a picture like this, and then identifying the boundaries of those. Okay, and those are going to be the critical values. So if you're using a right-tailed or left-tailed test, you'll only have one critical value. If you're using a two-tailed test, you'll have two critical values because you have two tails. Then those are the rejection regions. Then you compute the standardized test statistic, which in this case, it's basically the z-score of your sample mean. Okay, we know that in this case, because sigma is known, the sample means are normally distributed, the centered at mu, and the standard error of the means are going to be sigma over square root of n. So this is your standardized test statistic. And then you'll determine, is this number in the rejection region or not? And if it is, then you reject the null hypothesis. If it isn't, then you don't reject the null hypothesis. And then the last thing you do is write down one sentence saying, interpreting your decision in the context of the original claim. Okay. And that will be when you do that, you're going to be writing one of these four sentences. There's enough evidence to reject the claim, or there's enough evidence to support the claim, or there's not enough evidence to reject or support the claim. So you might want to keep this handy when you first start this out. This was the stuff from section 7.1. So those are the 8 steps to evaluating a claim about a population mean when sigma is known. So let's just do a couple of raw examples here, or a few examples. So in this first part, example 1, you want to evaluate a claim that mu is 40. Sigma is 1.97. So it's known. and the level of significance is 0.05. You take a sample of size 25 and you get a sample of a sample mean of 39.2. Now we are going to assume that the sample is random, and we're also going to assume that the population is normally distributed. So we need that. We need to assume that, otherwise the sample size is not big enough. Okay, so we'll assume the population is normally distributed. And if this was a more had more room on this paper, I would have said that. All right. So what we do is we've checked that. Then we want to write down our hypothesis, and because our claim has equality in it, that means this is our null hypothesis. And that's also our claim. And the alternative hypothesis says that mu is not equal to 40. Okay. So this is a two-tailed test. Okay. If this is true, if this hypothesis is true, then the unlikely values could be greater or less than 40. So we have a two-tailed test. So those are our two tails. And this combined areas need to be equal to sigma, which is, or equal to alpha, which is 0.05. So the area of this tail is 0.05 over 2, and so is this area. Okay. And this turns out to be 0.025. On your calculator. And if you, now what we really want to do is we want to find this boundary here, the boundary here. We're given that we've given an area, we want to find the boundary, so we use our inverse norm. Okay, and it turns out the inverse norm 0.025 is equal to negative 1.96, which we've almost seen that number before, except for the minus sign. Okay, so that's what this number is. Okay, and this is the standard normal curve, which is centered at 0. So this other value is going to be positive 1.96. Okay, all right. So these are our two critical values. Now I go ahead and test. Do a sample, compute the standardized test statistic, z, which is x bar minus mu divided by sigma over square root of n. Okay, this is x bar. Okay, so x bar is given. It's 39.2. Okay. All right, now what is mu? Well, we are assuming mu is equal to 40, right? That's that's our null hypothesis. So mu is 40. Then we divide by sigma over the square root of n, which is 25. Okay. Then you compute this on your calculator, and this is going to be negative 2.030. Okay. And in this case, in terms of how many decimal places you want, you just want to have enough to know whether this is in the rejection region or not. So we can clearly see that this will be in the rejection region. It's negative 2 is less than negative 1.96, right? So it's in the rejection region. So we reject H0. Okay. H0 is the claim, so we are rejecting the claim. So we say there's enough evidence to reject the claim. Okay. If z was between these numbers, then we would not have enough evidence to reject the claim. Okay. All right. Let's look at the next example. In this one, our claim says that mu is greater than or equal to 1475. Okay, our level of significance is 0.05 again, and our standard deviation is known. Our population standard deviation is known to be 29. Once again, our n is 26, so once again we'll assume that our sample is random and that the population is normally distributed, and that's our sample size. We took our sample and we got 1468. All right, now we can see that is actually bigger than this, or that's actually less than that. Is that enough to disprove the claim? Well, we don't know. We're going to find out. So we do the process. Our claim has some kind of equality in it, so once again, this has to be the null hypothesis. Our alternative hypothesis said mu is strictly less than 1475, and we just said this is our claim. All right, now, here, if this is true, our unlikely values would be less than 1475. So in this case, we're just using a left tail test. Okay, so this area is 0.05. And we can take our inverse norm of 0.05. And that turns out to be negative 1.645. Again, I think we've seen that number before. Okay, so that's our critical value. Okay, next we can do our test statistic. Okay. Now we will go ahead and plug stuff in. Now X bar we know is 1468. Now what is mu? Well, we assume mu is greater than or equal to 1475. So we can assume that because mu could be 1475, we might as well assume it. It turns out if we could also assume that mu is some number bigger than this, but it's going to turn out it works out because our critical value would still work if it would just be it works out. If mu is actually bigger than this, then this z would be actually less than what we computed if mu is equal to this. So if this number is in the rejection region, if mu is equal to 1475, it will still be in the rejection region if mu turns out to be greater than 1475. So that's why it works. So we can take mu to be 1475. Then we divide by 29, divide by the square root of 26. Okay. This turns out to be negative 1.23. Okay. And I only bring out, this is enough to tell us that this is not in the rejection region. This is like right here. Okay. So we don't reject H0. And that means we don't reject the claim. That's not enough to say that the claim is true. That we can support. We say that there's not enough evidence to reject the claim. Okay. All right. Let's go keep going. All right. With example 3, there's a claim that mu is not equal to 5880. We have a level of significance of 0.01, and sigma is 413. It's known. Our sample info, it says that our sample mean is 5771 and our sample size is 67. So this tells us our for all, and it's bigger than 30, so we know that the sample means will be normally distributed, so we can proceed. And our claim does not have equality in it, so this has to be the alternative hypothesis. So HA says that mu is not equal to 5880. Then the null hypothesis has to be the complement of that. Okay, and we said that this, we already know that this is our claim. Okay, so this means we're either going to be able to support our claim or not support our claim. Okay. Okay, so because if this is true, our unlikely values could be bigger or less than 5880. So we're going to use a two-tailed test again. And these two regions have to be equal to 0.01. So these two tails, the area of each tail is 0.01 divided by 2, which is 0.005. Okay. So that means that if we take inverse norm of 0.005, we get negative 2.575. Okay, and then this will be positive 2.575. Okay, I won't write it down, but we're using inverse norm of 0.005. Okay, so those are our critical values. Now we'll go ahead and compute Z. X bar is 5771. 71. Oops, sorry, let's try again. 5771. Mu we assume to be 5880. Okay. And then sigma is 413, so there's 413 divided by the square root of 67. And this turns out to be, on our calculator, turns out to be negative 2.16. Okay. And while it's big, it seems very negative, it's not in the rejection region. It's over here, right? So we don't reject H0. And that means there's not enough evidence. There's not enough evidence to do what? Well, we can't reject H0, so we can't support the claim. Okay, so we would say there's not enough evidence to support the claim. Okay. All right. Now let's look at a more word problem, or story problem, where we actually have some, or a word problem where we actually have some words to read. A random sample of 100 medical school applicants at a university has a mean score of 495 on the MCAT. According to a report, the mean score for the school's applicants is more than 499. Assume sigma is 10.6 at alpha equals 0.01. Is there evidence to support this claim? All right. Now, let's try writing this out. Well, in terms of equations, we have our our sample info says that n is 100, and our sample mean is 495. Sigma is 10.6. Alpha is 0.01. And our claim says that the mean score of all schools applicants is more than 499. So the claim says that mu is greater than 499. Okay. And okay. So let's see what happens here. So in this case, our claim is it has strict inequality, so this has to be our H0, or this has to be HA. Okay. H0 then says mu is less than or equal to 499. And the unlikely values then would be on the right. Would be the unlikely, if this is true, the unlikely values would be on the right. So this is 0.01. And then we can take the inverse norm. And let me just pause the video and calculate it myself. Yep, there it is. Here it's magically. So the inverse norm of 0.01 is negative 3.26, but we want the positive value here because it's a right tail test. Okay. So that's our critical value. So then z is going, again, x bar minus mu over sigma by the square root of n. So this is 495 minus 499, okay, divided by, what do we say, sigma is 10.6, divided by the square root of 100. Okay. And then if we compute that, okay, I'll compute that real quickly. 495 minus 499 is negative 4, divided by 10.6, multiply by square root of 100. That's negative 3.773. Okay, so that is going to be way, way over here. And then we can say, oh, that's way, way over here, but that's not in the rejection region, so we don't reject H0. Okay. And then that would be, so there's not enough evidence to, okay, so to what? Well, we're not rejecting H0, so we can't support the claim. Okay. So, and we do that, and that is, obviously we know ahead of time there was no way this could support it because 499 is actually bigger than 495 is less than 499. But you go through the process anyway. All right, so that's how we play the game. We're going to do lots of examples on your homework. Follow the guidelines, and I'll see you next time.